So hello everyone, my name is Andrey Norkin and I'm going to talk about AV1 productization and the royalty-free video codecs outlook. And in this talk I will be wearing two hats. One is of Netflix research scientist and another one of the co-chair of the codec working group in the Alliance for Open Media. And I got some signs to help you get who I'm speaking from at this moment. So first, AV1 productization at Netflix. When a new codec comes, it basically, there are several stages. First is the standardization, and then you have to wait for certain ecosystem support, and after that, the productization starts. And in general, productization involves a number of different things, like encoder vendor qualification, fine-tuning the parameters, A/B testing, catalog coverage, and also quite some things on the decoder side, such as device onboarding, certification, and other things. So when you're thinking about whether to to productize a new codec, you basically have to think about different aspects. Like first question probably you want to ask, does it enable new applications? Like, for example, 4K, HDR, or something else. You think about compression, whether you get better quality for your members, or maybe smaller, lower internet costs for some other members. The ecosystem, the device support at this moment and in the future. Also, the CDN. Typically, you get a CDN footprint increase if you deploy a new codec. Even if it's a good codec, because unless this codec replaces something else. So you have to take that into account as well. And the cost, including encoding cost, engineering cost for us, and some other costs. In case of AV1, basically the standard was finalized in June 2018. Our team contributed with test videos, film grant tool, the decoder model, and some other aspects like AVIF. After that, we engaged in SVT AV1. That was together with Intel team. That was the open source AV1 encoder, and we did it in order to increase AV1 adoption and also enable experimentation platform. We have done some early A/B test and pilot on AV1, and at that time, basically all the decoder was software, and we used David decoder on Android devices. You may know that at Netflix, when we use AV1, we always stream 10 bits, even for 8-bit content, because that gives you some gains. So we also funded a couple of rounds of optimization for the David decoder, one on our own and one together with Meta. And at some point, we enabled AV1 also using the hardware decoders. So after that, we started looking for AV1 on TVs, and we improved our certification process. We closed certain holes that we discovered, and we also started testing AV1 on browsers. First software decoding, and then a combination of hardware and software depending what's available on the machine. And also TVs, of course. So currently, all the AV1 certified devices, they prefer and stream AV1. And currently, AV1 is on for our new ingests, and we are increasing the catalog coverage. So another part of another standard related to AV1 is AVIF, which is basically AV1 intra in a container, so that you can compress images. And if you ever looked at Netflix app, you know that we have a lot of images on it. So it's important that they're compressed well, so that the interface is more responsive. So if you look at, for example, this content, that's the original. If you compress it too much with JPEG, you can certainly see some artifacts. If you compress it even more with AVIF, typically would look better. So we definitely see improvements. So the return on investment for AV1 is we see 10-point VMAF increase, 5% increase in 4K streaming hours, up to 38% reduction in quality drops, 2% reduction in start-play delay, reduce rebuffer rates, and network bandwidth. And you may ask, compared to what? And typically, it's compared to the codecs that AV1 replaces on these devices. So you can think about of a weighted average of other codecs that we have. So currently, AV1 is the most streamed profile on AV1-enabled devices, the second most streamed profile for non-HDR viewing across all the devices. And that comes after H.264, which is the most popular, or the most streamed standard so far. We have over 30% catalog coverage as of this month. And also, AVIF SDR provides time to render improvements, and we are testing it also on the mobile devices. So AV1 is great, but what's next, you can ask. We see improvements in metrics. Of course, the work is not finished, and we expect further deployments, like, for example, AV1 for HDR videos. Also, we probably are going to do some further fine-tuning of AV1 recipes, but what's coming after AV1? Will there be more efficient codecs and in the future? And the answer is coming from the Alliance for AOMedia, perhaps. And now I'm wearing another hat of the co-chair of the codec working group in the AOMedia. So we currently have a project which is studying further compression improvements after AV1, and this is called AOMedia Video Model, or AVM. That's a public project, so you can download it from GitLab and test it yourself. It's based, we took the code base from LibOM, which is the AV1 reference software. We cleaned it up, added a fixed QP offset mode, and instead of the rate control, removed some production code, and we started adding the AVM, so new tools, video coding tools. And of course, the software is in C, same as LibOM. It's done in the codec working group, and typically the process is such that if someone wants to propose a new tool, they bring the code, make it available to the group, a document that describes basically in the details what is proposed, and the test results on the common test conditions. And depending on the codec working group review, the tool either is adopted or the group is asking for some changes, and that's basically an iterative process. So the architecture for AVM is hybrid block-based, so similar as the previous generation of codecs. We have adopted about 90 experiments so far, and experiment is not a tool necessarily. It can be a small change. So the gains are varying, and actually some tools bring pretty big gains, but a lot of tools also bring smaller gains. So as usual. And you can think about AVM as a collection of tools or a toolbox that we are going to use for this process. So we are currently in the exploration phase. That means we haven't started writing the specification yet. So and we don't have the exact timeline. We also think that not every tool will end up in the future specification. Perhaps some of the tools would not get in, and maybe some would be modified. So far, all the tools that we adopted were traditional video codec tools, and we have been investigating some machine learning tools, and we continue to investigate them, and we'll see if they also get into the standard. Here is an example of what kind of tools exist in AVM. So those are new tools, basically, the changes. And these are not all the tools, because as I mentioned, there were 90 experiments, so it's difficult to fit everything in the in the flow chart. But you can see that, for example, there are some tools on partitioning, on interprediction, which is probably the most popular topic, also intra-predictional prediction, transforms, quantization. In-loop filters were pretty active area of research, and also coefficient coding and entropy coding. So I'm going to speak about 3 tools which I almost randomly selected. So I think one of them is just the partitioning. Also another one is would be useful if you're going to test AVM. And the other one, I just picked mine because I didn't need to draw a picture for it. So I already had it. So the first is the extended recursive partitioning. You know that in video codecs you have a block which is in AV1, for example, called a super block, which is 128 by 128 samples. You start subdividing it in the quad tree fashion. It can go down to 4 by 4 blocks or stop above that. But in AVM, we decided to remove some of these blocks, some of these partition types, and instead we added some more. So you can notice edge partitions and then 4-way unequal partitions at the bottom. And typically what it results in is that we get more flexibility in the partitioning, and it brings quite some gains. One other thing we changed that was a significant change was the quantization. So basically AV1 had bespoke quantization tables, and it had separate tables for AC and DC coefficients and for different bit depth. So the internal quantization index was from 0 to 255, but like external encoder parameter was from 0 to 63. So one of the first things we did is we tried to sort of make it clearer. And so currently we have the Q index, so dependency of the quantization step on the quantization index parameter is exponential, which is typically a good thing. In AV1 it was kind of exponential, but not exactly really. So the Q step doubles every 24 Q index values, and we also expose the internal parameter in the as a command line parameters for the encoder. So currently you can see that it's from 0 to 255, that's the range. And the quantization step is about similar to VVC, I would say, but it's kind of the granularity is 4 times finer than VVC. One other tool, like as I mentioned, there was a lot of work in-loop filters, including the cross-component filters. The deblocking has been changed. So basically AV1 had several different deblocking filters depending on the length. They were replaced by one generalized filter that is applied for any length of the samples. So this filter preserves details. So you can see in the figure, basically the blue line is the signal before the filtering. You can see some step there, and after the filtering, the step disappears, but some of the details are still preserved, and that's left for the low-pass operations in other filters. And basically, that improves both objective and subjective quality. Okay, but in the end, you probably would like to know what performance AVM has as of this moment. But before that, I have to say a couple of words about the common test conditions that we used for evaluation of the tools and also for tracking the codec performance. So we have 4 different configurations, all intra, everything is encoded separately, random access, typical like by prediction, and also a hierarchical frame structure, low delay, prediction is only from the past, and adaptive streaming, so encoding at several resolutions, several QPs, and then you build a convex hull. So we have quite many test sequences in our test set. Basically, there are about 69 mandatory sequences and 23 optional, including HDR and other content. Also, a variety of different types of videos, including like TV and movie-like content, animation, gaming, video conferencing, screen sharing, user generated content, and so on. So we use one-pass fixed frame offset QP structure, close GOP, 16-frame GOP size, and 6 base QPs. We calculate quite a bit of metrics, starting from PSNR and also VMAF and several others, and of course also encoding and decoding times. So here are the results. The most recent anchor is version 5 as of August this year. So basically the comparison is to the alternative AVM anchor, and that's basically AVM plus AV1 plus AVM quantizer. And we did it so that to approximately match the range of bit rates and to have similar, like basically to better compare complexity and and the range of bit rates. So you can see that if you look at the random access, which is and adaptive streaming, which are the most efficient encoding configuration, we have about 21.5% bitrate savings compared to AV1 on random access, and about 23 on adaptive streaming, and that's for PSNR averaged across 3 components. If we look at VMAF, we see somewhat better gains. So for random access, it's about 24.5% and 27% for adaptive streaming. Since we get better numbers on VMAF, we hope that that corresponds to better subjective quality as well. So you can notice that the encoding and decoding times are somewhat high, but you should also take into account that this is evaluated against a very well-optimized anchor. So even though, let's say, LibOM decoder is not as fast as David, but still it was quite well optimized, and some of the tools that are submitted, they're optimized, and some is mostly like research code, so we expect that the actual numbers are lower. Also, we have adopted new tools after this result, so we expect a new anchor in about more than a month, so we expect the more bitrate savings at that point. Wearing Netflix hat now, and we have contributed several things to this project, such as test sequences, libVMAF support for objective metrics, including VMAF Ambient. We implemented all the other metrics that are needed for the common test conditions, then some tools such as generalized deblocking filter, interdirection interpolation filter, improved ADST transforms, and we are currently working on debending and bending prevention, but that's under consideration, so it's not in the code base, at least at this moment. So if you would like to contribute to AVM, you have basically a couple of ways to do it. So first you have to decide whether what you want to contribute is a simple patch or if it's a coding tool. And if it's a simple patch like a bug fix, that's really easy. You sign the CLA and you can start contributing to the project. It's in a similar way as you can contribute to open source projects. If you want to contribute something more significant, then you actually it needs to be reviewed by the codec working group. So the best way is to join the codec working group. You can actually join. You can choose which working group you join in AOMedia, and then you can contribute tools, patches, participate in meetings, and so on. There is also some other approach. If you're a university and you're interested in a project on AVM, then you can actually find an industry partner who is the member of AOMedia, and then you can work on the projects and make submissions when you're ready. So you can find the AOMedia members on the AOMedia website. And that's the end of my presentation. Thank you. And yeah,